Stan Gibilisco here with Chapter 2 in A Tale of Two Antennas. This is a little bit of a theoretical discussion of what is taking place with the active tuning antenna system by Yaesu, which I have tuned for 40 meters on big number 8 Yaesu FT857D transceiver, powered by a 12.5 volt marine battery. Now there's something interesting about these batteries, deep cycle batteries, and maybe I'll get into that. But as they discharge, their voltage will gradually decline, and when it gets to about 12 volts even, it's about 50% discharge. That's when I will recharge this 35 ampere hour deep cycle marine battery. Now note that I do not have the transceiver grounded at this battery connection. It's entirely independent of the vehicle electrical system. The only ground that this system has is where the antenna meets the feed line, which is 10 feet of 50 ohm coaxial cable. The Yaesu active tuning antenna system mounted on the lip of the truck bed. And that's where the only ground is. Hopefully by doing it that way, I will avoid ground loops, which can cause all manner of grief with a system. And it seems to work, because if this thing will tune on 7 megahertz, actually I believe I tuned it on about 7.035, 7.025, something like that. If it'll come to a 1-to-1 standing wave ratio at that frequency, then I can be pretty sure, and it tunes, I've checked it, all the way from 10 meters down. I don't know if I checked it on 6 meters yet, but from 10 meters all the way down to 40, I'll get that thing will tune. So the ground system is all right, according to, as far as I know it is, as good as it can be with a vehicle. So that is the system. Now I tuned this until I got an SWR of exactly 1-to-1 for all intents and purposes. That means that the radiation resistance of this antenna element plus the loss resistance must equal a pure resistance equal to the characteristic impedance of the feed line, which is 50 ohms. So we know that the radiation resistance plus the loss resistance has to equal 50 ohms. That's the only way that you can get a 1-to-1 standing wave ratio, is to have a purely resistive impedance at the antenna that matches the characteristic impedance of the line. When you have a higher standing wave ratio, there are infinitely many combinations of resistance and reactance that can produce such a ratio. But for 1-to-1, it's got to be that. Now we can figure out what this radiation resistance is. This antenna is about 5 feet tall. Now let's do a little bit of calculating, shall we? I don't know how well you're going to be able to see this display. I'll move it up so you can see it. Now, what is the wavelength at 40 meters, or at 7 megahertz? Well, in free space, a wavelength is equal to 984 divided by the frequency in megahertz. That is the wavelength in feet. 140 feet, roughly. We're a little above 7 megahertz, so let's say that it's 140 feet. Now, if we divide 5 by 140, we get 0.0357 wavelengths. That's how long this thing is. That is pretty doggone short. Now, what's the radiation resistance then? Well, if you'll go back to my book, The Handbook of Radio and Wireless Technology, published way back in the 1990s, Stone Age. But some of these formulas still apply. They don't change with time. And this is one of them. The height and wavelengths of a vertical antenna fed against ground versus the radiation resistance. Now again, the number of wavelengths is only about, say, 0.04. Well, here is 0.1 would be about there, right? 0.2, 0.1 would be about there, 0.05, 0.04, 0.03. It's about an ohm. The radiation resistance of this thing is about 1 ohm. This is a graph from page 111 of my Handbook of Radio and Wireless Technology, and this is commonly available information. Radiation resistance in ohms. There's 0.05, 0.1, 0.15, 0.2, 0.25, so 0.05 would be about there, maybe about an ohm and a half. Let's just say, for the purposes of calculation here, that it is 1.5 ohms. Radiation resistance equals 1.5 ohms. Remember that the radiation resistance plus the loss resistance has to equal 50 ohms, meaning that the loss resistance here is 48.5 ohms. So the lion's share of this resistance that this system sees at the feed point is loss resistance. Now, what is the efficiency of this system? Well, the efficiency, pardon me, I'm having a little bit of difficulty, aren't I? The efficiency is equal to the radiation resistance divided by the total resistance, and that is this, 50 ohms. So the efficiency of this system is 1.5, that's the radiation resistance, divided by 50, which would be 3.0 divided by 100. You can do that in your head. Just multiply both the numerator and the denominator by 2. 3/100ths, or 3%. We know by theoretical calculation that that is how efficient this ATAS actually is. Now, before I start disparaging Yaesu and telling him they've gotten a rotten system here, let me hasten to say I don't know that much about the tuning network in this thing. It could be that there is, in fact, some other kind of system in there that will somewhat mitigate this situation, but the fact is that the physical length of the antenna is what it is. And unless we have some sort of a very sophisticated matching network in there, we're going to see 3% efficiency. Now, as for my force-fed whip, it's not going to be a heck of a lot better. But the advantage of this system is that the SWR on the feed line back here, the SWR here is 1-to-1. So we're going to get minimal loss in this line. The loss is going to take place in the miserable ground system of big number 8. How they managed to get a 1-to-1 standing wave ratio, and I can't imagine that that thing is any more sophisticated than a simple tunable inductor. But maybe I'm wrong. Maybe I'm wrong. If I am wrong, tell me. Tell me what's in there if you happen to know. But as far as I'm able to tell at this point, the efficiency of this system is 3%. So if I'm putting 30 watts in there, I'm only getting about less than 1 watt of actual radiated power into space. But as you know, if you've done much ham radio work, you can make contacts with a dummy load. we'll see. We'll put it on the air and we'll find out. We'll compare this. Now I'm going to go through the theory of my other antenna, the force-fed whip, and see how efficient that is in theory. Then we'll get on the air and see which one really wins. Stan Gibilisco, W1GV Whiskey 1 Golf Victor. Until next time, 73, and so long.